on optimal growth to transition next door, led by Lorette. And then there will be one on scaling of Reynolds stress tensor components by Joseph Vicky, and this will happen here, expecting that the larger crowd will be interested in the scaling, but I guess so. We move on to the last two talks of today. The first one will be given by Fernando Mellibovsky, continuing sort of the transitional story in pipe flow on the large-scale structures in transitional pipe flow. Please.
Thank you. I want to thank everybody because most people must be thinking already of the dinner tonight. But well, I'll stick to pipe flow, and what I'll be looking at is transitional pipe flow. So these edge states that we've been talking about in many talks these days, and particularly in long pipes of 50 diameters long, where these edge states tend to remain localized. Okay, I'll start with a short introduction. I'll skip most things of the introduction because they've already been said in other pipe flow presentations. Then I'll say some words about the problem formulation that we're using and the numerical approach we are taking. Then I'll explain the specificities of the way in which we compute critical trajectories, the edge trajectories that we've been seeing these days. And then for the long pipe, I'll present results. I'll show that these states remain localized even when transition is to delocalized structures such as slags or growing paths. I'll compare one of these edge states at a fairly low Reynolds number with its supercritical counterpart, its turbulent counterpart, which is a puff. And then I'll show a couple of videos for this, for the edge state and the puff to see what the differences are, how they obey to different spatial coherences. And finally, I'll show some results on a Reynolds dependency analysis of these structures. I'll end up with some conclusions. Okay. So as an introduction, just say that, well, as you all know, the pipe flow is linearly stable for all Reynolds numbers. So we need, here I plot amplitude. This zero amplitude axis corresponds to the basic flow. And we need to finite amplitude perturbations to trigger transition. So in this 2D plot, this line here would be the critical threshold. In reality, since it's an infinite dimensional space, it would be an hypersurface with folds and maybe some holes that allow for relaminarization even at high Reynolds number. Many solutions have already been found in the form of traveling waves, now some relative periodic orbits too, and their lower branches seem to play an important role in transition. But as we'll see in the long pipes, they are not clearly seen, at least not in the way they are seen in short pipes. Okay, so what I'll do is a direct exploration of phase map. So we'll be looking for things in phase map, solutions in phase map. And we'll do this search, but restricting ourselves to the boundary between the basins of attraction of the basic flow and of the laminar flow and the turbulent flow. So this, the edge, the critical threshold. We'll search for the saddle that is embedded within this critical threshold, which in the case of the long pipe, we've seen these days. In fact, Johan Duguay already showed some results in a short pipe, where we see that this chaotic saddle can be found, and in fact, there exist underlying traveling wave solutions that can sort of explain, in terms of their the number of unstable directions that it has, its chaotic behavior. but we'll now focus on long pipes, and we'll base the study on localized pair of rolls, which I'll show in. I'll show next. So as the problem formulation, we're dealing with non-dimensional Navier-Stokes equations for a perturbation on the basic flow. And it's not pressure-driven flow. What we'll be dealing with is with constant mass flux flow. In fact, we add here an axial forcing that is recomputed at each time step to keep the mass flux constant. So we define our Reynolds number in terms of the mean axial velocity of the flow, the diameter, and the kinematic viscosity of the fluid. As to the numerical method, we use solenoidal spectral Petrov-Galerkin discretization, Fourier in the azimuthal and axial direction, and then Chebyshev in the radial direction. Finally, we use a fourth-order backward difference scheme to time-step the solution. Okay. The method. What is the method we use to compute these, to track these critical trajectories is basically the same one that has been used by Duguay, a bit simpler even. What we do is we start with an initial condition, which is a localized pair of rolls in our case, and we scale this initial condition up and down until we bound an initial condition, we bound the trajectory on the critical threshold. So we've got one that goes turbulent. It's longer word. We bound trajectory between a turbulent trajectory and one that decays back to laminarity. We run both trajectories simultaneously. They are close one to the other. And when they grow apart by more than a tolerance, we run a bisecting case and check whether it goes turbulent or laminar, and we keep doing this bisection and shooting method to remain always on the critical threshold. And what happens is that after a long transient, here at Reynolds 1900, after a more or less long transient, we end up with a chaotic behavior, like you can see here, where the dynamics have been attracted by a sort of saddle within the critical threshold that we call the edge state. So the critical trajectory that we were seeing in the previous slide, so somewhere here, in fact, at the end of it, the black line is what I represent here. These are energy contours, iso contours. So if we look at the energy distribution as a function of the length of the axial coordinate, we see the black line that the structure is localized. We can see here a maximum where the energy is maximum, and then exponential decay at both sides. When we compare with a path, a turbulent path, so a trajectory that has gone turbulent, we see that we've got also exponential decays, but with a sharper trailing edge and a more extended leading edge. This is the first difference we can see between the edge state and the turbulent state to which it leads at Reynolds 1900. So another thing we've done to compare both states is we've plotted the purely axisymmetric energy. This is the red line as a function of the axial position, and also of the non-axisymmetric mode, so the purely 3D mode. And we can see that both the edge state and the edge state and the turbulent path are fairly axisymmetric towards the leading edge, towards the front, but highly non-axisymmetric in the back. We'll see this, we can see it here, and not so much in the path where the trailing edge is sharper. It's clearly sharper.
If you went to slightly higher Reynolds number, do you see bigger differences between the critical?
Yeah, we will get to that. So for the time being, we stick to this Reynolds 1900 simulation. Here we've got the path the edge state that we pick from half the plot energy plot that I showed before, and for 400 time units. And what we see is that it's dynamically active. Oops, sorry. Okay, I think it takes some time to start. It is very dynamically active, so it's nothing like a traveling wave, or doesn't settle on, but it remains chaotic. But we can see some coherence in some cross sections across it. Okay. It remains always fairly short, the same characteristic length, and it remains so forever. If we pick this edge state and let it evolve towards turbulence, so we pick the edge state and allow it to go turbulent, we see how the path develops, how we lose coherence. This we can see in this cross section. We can see some coherence from time to time, but the length of the structure is clearly longer, and the spatial coherence is lesser. So now, answering what you asked, what we've done is Reynolds sensitivity analysis. So we've checked the dependency of some global parameters of these states as a function of the Reynolds number. Here we can see the turbulent states to which they lead. This is energy against time for several Reynolds numbers ranging from 1800 to 2800. And here are the corresponding critical trajectories. And we can see that, at least in terms of energy, there is no much difference in the energy contents of these edge trajectories within this Reynolds range. We'll see now that why there's a gap between 2000 and 2200 in the energy of the turbulent state. So over this long time series, what I've done is we've taken statistical properties rather than at a time instant, because they are dynamically active. And what I'm plotting here is the time averaged energy against Reynolds number, for the several Reynolds number, and for the turbulent state, the edge state, and the initial condition from where we landed, the initial condition that we need to pick to land on this critical threshold, okay, on the edge state. For the turbulent state, a remarkable thing is that there's a gap, there's a jump, an energy jump between Reynolds 2000 and 2200. Okay, this I'll explain in terms of the structural length later. For the edge state, we can see that it remains fairly constant, the energy, whereas the initial condition that the initial condition we picked at each Reynolds number that landed on this critical regime on the edge state decreases as a function of Reynolds, which means that the stable manifold of the edge state extends at very low energies. And the stable manifold, the critical threshold extends to very low manifolds capturing flow fields towards criticality. So back to this jump in energy, the explanation comes from the delocalization of the paths. Up to Reynolds 2000, the length of the structure that we measure from the energy distribution are localized. The paths travel downstream, but don't grow in size. From Reynolds 2000 and up, the structures grow unboundedly and end up filling the whole domain. So we got transition rather to slag type structure. Whereas the edge state doesn't change in size very much in this Reynolds range. Forget about this advection speed plot. The error bars are wrong. I've got to redo it. But the thing is that the edge state doesn't change very much. Its advection speed, while being faster than the corresponding paths. Of course, the slugs I cannot compute an advection velocity because they fill the whole domain. And are faster where the paths travel at an average advection speed about the mean velocity of the flow. As to the friction factors, we can see here that the edge states are not laminar, but behave very much like the laminar profile. You see that while we computed these friction factors on the structure extent, not for the whole structure. So not for the whole pipe, just for the extent where we've got structure. As to the turbulent state, from when we go from paths to fully developed turbulence filling the whole domain, we've got this characteristic jump. Well, now to the conclusions. I wanted to say some things about short pipes. In fact, that we'll forget about this. In fact, it's what we've seen from Johann's talk. And just add that for the long pipe, we've got localized critical trajectories, even at regimes where transition is to non-localized turbulent structures. Within the Reynolds range studied, there is no clear evolution of the states. Runs at higher Reynolds would be needed to see if the length changes, the advection speed, or something like that. And feeding these states, these localized edge states into the Newton method, haven't produced traveling wave solutions that, like the one converged directly in this 2.5D model at Reynolds 10,000. We haven't been able to converge any traveling wave solution in the Reynolds range, at least studied in a fully resolved pipe. My intuition is that the underlying solutions would rather be relative periodic orbits, something like pulsating or maybe modulated traveling waves, but we cannot know. And then just that the relation between short pipe and long pipe, this the relation between periodic solutions like the exact traveling waves and so on with this long pipe localized structure needs to be yet clarified, because it's not really clear how we go from infinitely periodic structures to localized structures.
Could you go back to the Reynolds number sensitivity plot?
Yes.
In the upper right-hand corner there, you show something that goes to the supercritical, and then you have one that's in the critical state. And at the beginning, their error bars overlap, which
Yes.
is interesting because that suggests there's something sort of special that happens dynamically that sets it off one way or the other. Do you have any inkling of that? I mean, what makes it grow? The length scale grow?
Yeah, in fact, it's not that grows, but that for some reason it's least stable. It fluctuates a lot.
Uh-huh.
So,
Did you have an idea what triggers that? Because
No, I
they're
have
both
no
starting
idea
very
so
close
far.
initial conditions there, if you want to think of it that initial.
uh-huh. Yeah, no, I haven't checked the.
Early on, you showed some energy distribution of the
Yes.
length of the pipe. I didn't see any feature really that allows you to say, well, it's short or long. I mean, everything depends on your level you want to cut off, right?
Of course, because it's an exponential decay. Yeah, we take criteria, and then, in fact, what I take is 98%. So I don't cut.
So what would happen if you choose 200? It would overlap and just keep going down, or it would sort of adjust its size?
What do you mean?
It would
in length?
go
Yeah.
down to lower energy, so that you would see.
think
It
so.
would probably adapt a bit because it's not. I mean, the decay, it's not huge in this.
Yeah, that's what I'm asking.
But it would probably adapt a bit, but it would still be localized in the same. Yeah.
We're a bit behind, so it's great.
What's the connection between these critical trajectories and the unstable periodic orbits that others have talked about? Is there any connection?
Still to be clarified, in fact. I mean, we would. We'll discuss this later if you want.
If you have a question that just a brief answer,
I mean, did you explain why there was a jump in energy? You said you will explain it later. Did you actually do it?
Yeah, you see it in the, because in fact it comes from the fact that
Yeah, that jump.
the structure, the length of the structure grows unboundedly and fills the whole domain. That's why the energy. So the energy normalized by the length of the structure remains fairly the same. But
Do I understand right that you have 100 diameter, it's 100 diameter pipe?
no, 50 diameter.
50 diameter, and you have 193 mode? 190, what's your resolution in?
It's 193 points.
193 points.
okay, and that can also be discussed.